Welcome to part 3 of electrostatics. In this session we discuss about the different types of charge distribution, electric flux and its properties, the Gauss's law and its applications. First we discuss about the continuous charge distribution. We usually deal with charges greater than that of an electron. Thus we imagine that charges are spread in a region in a continuous manner. This charge distribution is called continuous charge distribution. Linear charge density. If a charge Q is distributed uniformly over a length L of wire, then linear charge density is lambda equals Q by L. Unit is coulomb per meter. Now about surface charge density. If a charge Q is distributed uniformly over an area A, then surface charge density sigma equals Q by A. Unit is coulomb per meter square. Again, volume charge density. If a charge Q is distributed uniformly over a volume V, then volume charge density rho equals Q by V. Unit is coulomb per meter cube. Electric flux. The electric flux through a surface is defined as the total number of electric field lines passing normal to the surface. Mathematically, it is represented as phi equals integral E dot ds. It is a scalar quantity. Gauss's theorem. The total flux through a closed surface is 1 by epsilon 0 times the net charge enclosed by the closed surface. It is mathematically expressed as phi equal integral E dot ds is equal to Q by epsilon 0. Now we are going to prove the Gauss's theorem. Consider a sphere of radius r and a charge is located at its center. Electric field at any point on the surface of the sphere E equal 1 by 4 pi epsilon 0 into Q by r square. But electric flux phi equal integral E dot ds. That is phi equal E into integral ds. That is phi equal E into total area of the sphere. That is phi equal 1 by 4 pi epsilon 0 into Q by r squared into 4 pi r squared. That is Q by epsilon 0. This is the theorem. Now we are going to discuss the various applications of Gauss's law. Number 1. The field due to an infinitely long straight charged wire. Please refer the diagram. Consider a uniformly charged wire with a linear charge density lambda. Let P be a point at a distance r from the wire and E be the electric field at P. Imagine a Gaussian cylinder of any length L and radius r with a line charge as x. The electric field and the surface vector are perpendicular to each other at the end faces. Hence, the total normal flux through the end faces is 0. The flux through the curved surface of the cylinder is equal to integral E dot ds is equal to E dot integral ds. That is E into 2 pi r L. The charge Q enclosed by the Gaussian cylinder of length L, Q is equal to L lambda. According to the Gauss's theorem, integral E dot ds is equal to 1 by epsilon 0 into Q. Therefore, E into 2 pi RL is equal to L lambda by epsilon 0. Therefore, E is equal to lambda by 2 pi epsilon 0 R. That is, if a line charge is positive, then the field is outward. If a line charge is negative, then the field is inward. Now we are coming to the second application of Gauss's theorem. the field due to a uniformly charged infinite plane sheet. Please refer the diagram. Then consider a uniformly charged infinite plane sheet of surface charge density sigma. Let P be a point at a distance r from the sheet and E be the electric field at P. Consider a small circular area around P and parallel to the sheet of charge. Please refer the diagram. With this area as one of the end faces, construct a Gaussian cylinder of length 2r passing through the sheet. The electric field is always perpendicular to the sheet and directed away from it. The electric flux through the curved surface of the cylinder is 0, since the electric field is perpendicular to ds. Therefore, total flux through the end faces is equal to Ea plus Ea is equal to 2Ea. The net charge enclosed by the Gaussian cylinder is equal to A sigma, where A is the area of the end face of the cylinder. According to Gauss's law, electric flux is equal to charge enclosed by epsilon 0. Therefore, 2Ea is equal to A sigma by epsilon 0. Therefore, E equal sigma by 2 epsilon 0. Thus, the field is independent of distance of the point from the sheet. Now we are coming to the third application of Gauss's theorem. The field due to a uniformly charged spherical shell. Please refer the diagram. Consider a uniformly charged spherical shell with a radius r with a surface charge density sigma. Let P be a point outside the shell at a distance small r from the center. Consider a Gaussian surface of radius small r and concentric with the shell. The total electric flux through the Gaussian surface is equal to integral E dot ds is equal to q by epsilon 0. Again, area of the Gaussian surface is equal to 4 pi small r squared. Net charge enclosed is equal to sigma into 4 pi capital R squared. According to Gauss's law, the total electric flux passing through the Gaussian sphere is equal to net charge by epsilon 0. Therefore, E into 4 pi small r squared is equal to sigma 4 pi capital R squared divided by epsilon 0. Therefore, the intensity of the electric field at P, E is equal to sigma capital R squared divided by epsilon 0 small r squared. But sigma is equal to q by 4 pi capital R squared. Again, E is equal to sigma capital R squared by epsilon 0 small r squared. On substituting the value of sigma, E is equal to capital R squared by epsilon 0 small r squared into q by 4 pi capital R squared. On simplification, we get E is equal to 1 by 4 pi epsilon 0 into q by r squared. Therefore, this field is equivalent to that due to a point charge. Special cases. Case 1. If the point P is on the surface of the spherical shell, capital R is equal to small r. Therefore, E equal 1 by 4 pi epsilon 0 into q by r squared. Again, case 2. If the point P is inside the spherical shell, charge enclosed is equal to 0. Therefore, the intensity of electric field inside the charged spherical shell is 0. This is called electrostatic shielding. The disappearance of electric field in the cavity in a charged conductor is 0. This property is called electrostatic shielding. The major application of this is that during lightning, it is better to sit inside the car than standing outside.